All right, today we're doing something that feels a little bit like magic. We're going to take some simple powder and liquid and turn it into a tool that lets us see a picture of DNA. Making an agarose gel isn't just another step in a protocol. It's like you're creating a canvas that's going to reveal the unseen world of genetics. So let's get into it.
Think about this for a second. You've got a tiny tube with a mix of DNA fragments inside. They're all different lengths, all jumbled together, and they are completely, utterly invisible. So how in the world do you sort them? How do you figure out what you've actually got in there?
Well, the answer is it's brilliant. You build a sieve. Not for sifting flour, but a microscopic one designed to sort molecules. It's a simple idea, right? But this one analogy is the key to understanding this entire powerful technique. So this molecular sieve, that's our agarose gel. And the whole process is called agarose gel electrophoresis. I know, it's a mouthful, but the concept is super straightforward. We use electricity to push the DNA through our gel. Since DNA has a negative charge, it moves toward the positive end. The small bits of DNA, they zip right through the holes in the sieve. But the big, bulky pieces, they get tangled up and move a lot slower. Simple as that.
Okay, this is where it gets really important. The picture you get at the end, how sharp and clear those DNA bands are, well, the quality of that picture is determined right now, at the very beginning. It all comes down to crafting the perfect gel matrix. So what's the number one variable you control? It's the percentage of agarose you use. As you can see here, different percentages are for different jobs. If you're looking at huge pieces of DNA, like whole chunks of a genome, you want a low percentage, like a 0.5% gel. But if you're trying to separate tiny little PCR products, you'll need a much denser gel, maybe a 2.0%, to see the difference between them.
So what does percentage actually mean for our sieve? It's all about the size of the holes, the pores. A low percentage gel is like a net with really big holes. It's kind of floppy and fragile, but it's great for separating huge molecules. A high percentage gel, on the other hand, creates this dense, tight mesh with tiny little pores. This gives you amazing resolution for small DNA fragments. So it's always a trade-off. All right, let's get our hands dirty. How do we actually make this thing? Step 1 is just like baking. You follow the recipe. First, you measure out your buffer, TAE or TBE, we'll get to that later, into a flask. Then you do a quick calculation to figure out how much agarose powder you need for the percentage you want. You weigh it out, dump it in, and give it a good swirl to break up any clumps.
Okay, recipes mixed. Now for the fun part, melting. A microwave is your best friend here, but you can't just set it for 5 minutes and walk away. You want to heat it in short bursts, carefully taking it out to swirl in between. And your goal is to get a solution that is 100% clear, like crystal clear, no little specks floating around. That's how you know all the agarose has dissolved, and that's critical for creating a nice, uniform sieve. Whoa, hold on. Before we go any further, we have to talk safety. This is a big one. This agarose solution can superheat in the microwave. That means it can get hotter than boiling without actually bubbling. Then when you pick it up and swirl it, the whole thing can erupt violently out of the flask. So please always use heat-resistant gloves and never point the flask at your face. Seriously. Okay, safety briefing over. Here's another super critical step, and it's one where a lot of people mess up. You have to let the solution cool down before you pour it. If it's screaming hot, it'll warp your plastic casting tray and your gel will be useless. But if it gets too cool, it'll start turning into a glob right there in the flask. You're aiming for that sweet spot, around 50 to 60 degrees Celsius, warm enough to comfortably touch for a second. All right, our solution is at the perfect temperature. Now we get to actually cast the gel. This is the part where we physically build the stage for our DNA race, and paying attention to the details here makes all the difference. First things first, prep your mold. You'll seal the ends of the tray with dams or just some good old-fashioned tape. And I cannot stress this enough, put it on a surface that is perfectly level. If your bench isn't level, your gel won't be either, and your DNA will run crooked. Then you put in the comb that makes the little wells, making sure the teeth are up off the bottom just a tiny bit. Okay, deep breath. Time to pour. Go slow and steady, pouring the agarose into the tray. You're trying to avoid making bubbles. But hey, it happens. If you get a few, no big deal. Here's a little pro tip. Just take a clean pipette tip and pop them. Then, the hard part, walk away. Just let it sit undisturbed for 20-30 minutes. You'll know it's ready when it turns from clear to a cloudy, opaque color. Of course, sometimes things just don't go according to plan. Maybe your gel leaks all over the bench. or the wells get all torn up when you pull the comb out. It happens to everyone. That's what a guide like this is for. It helps you figure out what went wrong, like maybe your tape wasn't sealed well, and tells you how to fix it for next time. It's all part of the learning process. Our gel is set. It's solid, the wells look great. Now it's time for the main event. I like to call it the DNA race. We're about to load our samples and hit the power. So every race needs a racetrack, right? Well, in our case, the buffer that you run the gel in is the racetrack, and the type you choose actually matters. If you plan on cutting your DNA out of the gel later to use it for something else, you'll want to use TAE buffer. But if you need really sharp, high-resolution bands for small DNA fragments, TBE is the way to go. It just holds up better during long runs. But why does the DNA even move? What's the driving force behind this race? It's just basic chemistry. DNA has a phosphate backbone, which gives it a negative charge. It's just naturally negative. So when you put it in an electric field, it's going to run away from the negative pole, which is black, and sprint towards the positive pole, which is red. Just remember, run to red. All right, so if the buffer is the track, the voltage, that's your gas pedal. That's the speed limit for the race. You could crank the voltage way up to get it done fast, but you risk generating a lot of heat. That heat can actually start to melt the gel and make your bands look distorted and smeared. We call them smiling bands. Going slower with a lower voltage takes more time, but it gives you much sharper, prettier results. A good rule of thumb is about 5 to 8 volts per centimeter of gel. The race is over, the power is off, and we have our final picture. But a picture full of bands doesn't mean anything by itself. It's like looking at a map with no scale. We need a ruler to actually measure what we're seeing. That ruler is called a DNA ladder. It's basically a pre-made cocktail of DNA fragments where we know the exact size of every single one. We run this ladder in a lane right next to our own samples. Then, we can just compare our unknown bands to the known bands in the ladder to get a really good estimate of their size. It is an absolutely essential part of every single gel. And just like you wouldn't use a yardstick to measure something tiny, you need the right ruler for the right job. There are all kinds of ladders. A 1 kilobase or 1 kilobase ladder has bands that are good for measuring larger DNA fragments. But if you're looking at small stuff, you'd use a 100 base pair ladder. You just pick the ladder that has a good range of sizes for what you expect to see in your sample. And to make sure your ruler is accurate, you gotta treat it right. So here are a few quick pro tips. Use the right amount. Too little and you won't see it, too much and you get a big smeared blob. You should also store it frozen at -20 degrees Celsius. And it's a good idea to divide it into smaller tubes so you're not constantly freezing and thawing the whole stock, which can mess it up over time. And that's really all there is to it. You started with a scoop of powder and some liquid, and you ended up creating a high-precision tool that let you visualize the building blocks of life. It's an amazing process. So now that you know how to see the invisible, what will you go out and discover?